everyone. Today we are going to start chapter 11, which is on energy. So these are the notes for section 11.1, energy and its conservation. So our learning targets today are to know that energy causes a change in the environment, that energy comes in many forms, and that energy can be quantified. That means we can calculate it. And our questions we're going to try and answer today are, what is energy? What is potential energy and how do we quantify it? What is kinetic energy and how do we quantify it? So let's go ahead and start with this idea about energy. So energy is one of those terms that you hear a lot, right? Lots of people say, oh, I don't have any energy, or oh my gosh, my energy is so low, or oh, I need a nap to get some energy. So in physics, it has a very specific definition. So in physics, we are going to say that energy is the ability to change an environment. Now, usually when you say environment, you think about, going out in the forest or something into the environment. But we want a much more general sense of environment. So any change on an environment, you pick up a desk, you move a stool, you run a race. Okay, so any change in your environment. All right. Energy comes in lots and lots of different forms. So I have some examples here. See if you can think of what each of these forms are. So this first picture, this is a match. What kind of energy would you have in a match? This is an example of chemical energy, right? There's sulfur chemicals on the head of the match, and when you apply friction, they start to burn. This is the sun. Yep, this is light energy. Good for you. The same kind that makes solar calculators and solar panels work. What's this? This is nuclear energy. Nuclear energy comes in a real destructive form, which is an example of this, and it also comes in nuclear power plants that we use to generate electricity. What about this? This is an example of wind energy, right? These are wind turbines that are also generating electricity. All right, what have we got down here? Yep, this is good old electrical energy. What about this one? This is heat energy. Good for you. I don't know why I wrote energy on that one. What's this? This is hydro or water. Okay. So all of these things are different kinds of energy, and they all have the ability to change their environment somehow. What we're going to focus on in physics are the two types of energy that are gravitational potential energy and kinetic energy. All right, so those are the two that we are going to spend the most time talking about. We will, hit some of these others as well, but mostly we're going to talk about gravitational potential energy and kinetic energy. Okay, so let's start with gravitational potential energy. What is gravitational potential energy? Gravitational potential energy is the energy that is stored. That's important, right? Because potential means stored. You have the potential to use it or to do something with it. The energy that is stored by an object as it moves against gravity. How does something move against gravity? Well, usually that means you're going to lift it up, right? You're going to pick it up. Gravity works down. If you pick something up, it's going against gravity. So the energy that's stored by an object as it moves against gravity, that's gravitational potential energy. So here we have a couple of pictures. This is a person who is bending over to get this box and then lifts it up. So let's think about this for a minute. If this is the ground, right? This is the ground right here. And this box is sitting on the ground. What kind of potential energy does it have? Yeah, it doesn't have any, right? So we can say that the potential energy, PE, that's potential energy, of this box right now is 0 because it's sitting on the ground. We haven't lifted it at all, right? So there's no energy for it to store. It hasn't moved against gravity yet. Well, what about here? Here's the ground, and this box is now up in the air. So does this object have gravitational potential energy? Yes, it does. This object has energy. I guess we should be more specific, shouldn't we? Has potential energy because it's been lifted off the ground. All right, so over here we have an object with no gravitational potential energy because there it is sitting on the ground. And over here we have an object that does have potential energy, gravitational potential energy, because we've lifted it off the ground. Okay? How much energy does the box have? See, you knew we were going to get to the numbers at some point, right? How much potential energy does this box have? Well, that's going to depend on two things. And first of all, it depends on the mass of the box, right? Bigger things are going to be able to store more energy than smaller things. Okay, so it depends on the mass of the box. But it also depends on the height that it gets lifted to. So if you lift something up higher, it has done more, it has gone further against gravity, and so it's going to have more stored energy. All right, hopefully that makes sense to you. So how would we calculate that? Well, so we would say PE, that stands for potential energy. PE is the mass times acceleration due to gravity, right? You got to get the gravity in there somewhere, times the height, so mgh. Please remember that as long as you're on the Earth, g is 9.8 meters per second squared. I suppose I should put the units there. All right. What units do we use for this? Well, these are going to be new units for us. Technically, they are kilogram meters squared per second squared, but it's much easier to think of them as joules, Joules. They are named after a famous physicist who did a lot of work in this area of energy. So we measure the potential energy in joules, and if you want, you can just say capital J. That's enough. All right? So let's see how this works. So we have an example problem here, and it says, the box being lifted in the example has a mass of 23 kilograms and is lifted to a height of 1.5 meters. That's good. Remember, we always want our mass in kilograms and we want our height in meters. And then it says calculate the potential energy stored by the box. Okay, we can do this. Not a big deal. So we know the mass is 23 kilograms. We know the height is 1.5 meters. It didn't tell us any differently, so we're going to assume that we're on the Earth. So we know that G is 9.8 meters per second squared. And so we've got potential energy is equal to mass times acceleration due to gravity times the height. So we've got potential energy is 23 times 9.8 times 1.5. If I multiply all that together, I get 338.1. Let's go ahead and round that to 340 because that seems like a nice round number to me, and we are going to call it joules. Okay, so here's our final answer. This box has stored 340 joules of energy. 1 joule is a pretty small amount, so this is actually not a lot of energy that we've stored here. Okay? All right, your turn. So go ahead and shut the recording off. Try part A and part B here using that potential energy formula. All right? And when you are ready to go on, you can turn it back on. All right, I hope that was successful for you. If not, you can ask about it in class next time. So here we have kinetic energy. This is the second type of energy that we're going to focus on in class. So what is kinetic energy? Potential energy, remember, was energy that was being stored. Kinetic energy is energy that's being used, and it's being used because the object is moving. So we call this the energy of movement. Anything that's moving has kinetic energy. Okay, it has energy, it's using it, it's changing its environment, right? Moving through the air, moving across the ground, moving through the sky, something. Okay, so here are some examples. We have a train. The train is moving around a track. Does this have kinetic energy? Yes, it does. This has kinetic energy. Ke is kinetic energy because it's moving. Doesn't matter whether it's moving in a circle or a straight line. Okay, what about this picture? This is Allison Felix. She is an amazing track athlete, did great things at the Olympics in 2016. Does Allison Felix have kinetic energy? Yes, she does. She has kinetic energy because she is also moving. Okay, and finally we have a baby elephant here. Isn't it cute? Does the baby elephant have kinetic energy? Yes, it does. Good for you. Because the baby elephant is trotting there through the jungle, and the important thing is that the baby elephant is moving. Okay, anything that's moving has energy. All right, how much energy does it have? Well, if I were to ask you, which of these objects up here, the train or Allison Felix or the baby elephant, has the most kinetic energy, what do you think we would need to know? What does kinetic energy depend on? All right, so hopefully you recognize that the mass is also important here. So my kinetic energy depends on the mass, right? Because bigger things are still going to have more energy. And it also depends, the energy of movement, what do you suppose it's going to depend on? Yeah, it's going to depend on the velocity, right? How fast is this thing going? The faster something's going, the more energy it has. Okay, hopefully that makes sense to you. So how would we figure that out? Well, kinetic energy, Ke, is 1/2 mv squared. Now, if you look at that really carefully, you are going to notice that the velocity is more important than the mass in this formula. How do I know that? Right, because the velocity is squared. Okay, so the velocity is going to have a bigger impact on the energy than the mass. The mass is important. I'm not saying it's not. I'm just saying that the velocity has a bigger impact. We are also going to measure this in, you got it, joules, or just J if you'd rather. Okay? All right, so here's our example problem. A baby elephant with a mass of 91 kilograms is running at 3.5 meters per second. Calculate the kinetic energy used by the elephant. Okay, so let's see how we're going to do this problem here. So I know that the mass of this baby elephant is 91 kilograms. I know the velocity of this baby elephant is 3.5 meters per second, and I am trying to find the kinetic energy. So Ke is 1/2 mv squared. Let's plug in what we know. Please notice that it is only the velocity that gets squared, right? It's not the whole thing, it's just the velocity that gets squared. And order of operations says I have to do the squaring first. So I'm going to do 3.5 squared, and that's going to give me 1/2 times 91 times 12.25. Okay? And then I'm going to go ahead and just multiply from right to left. So I'm going to say 0.5 times 91 times 12.25, and I'm going to get a kinetic energy of 557.375. I'm going to round that to 560 because that's a nice easy number. Joules. And so my object has 560 joules of energy as it's moving. If I really wanted to compare, I would need to know Alice and Felix's mass, and I would need to know the mass of the train, and then I could and their speed, right, and their velocity, and then I could figure out which of those examples has the most energy. Okay, your turn. This car, 870 kilograms, starts out at 22 meters per second and speeds up to 44 meters per second. I would like you to find the starting kinetic energy when it's at 22, and the final kinetic energy when it's at 44. All right? So, as always, if you have questions, make sure you write them down so that we can talk about them in class next time. And this is your introduction to energy. Thank you very much. I will see you in class.